For the last part of today's lecture, we're going to talk about private aggregation of teacher ensembles, or as it's sometimes cutely called, it's called PATE. So this was an approach introduced by Papernow et al., that is Papernow, Abadi, Erlingson, Goodfellow, and Talwar in 2017. And then there's another work that was sort of a follow-up work by the same group, which was, again, Papernow et al. That was in 2018. And these are kind of the more like practical, applied type methods. There's also a paper by a different group by Basili, Sakar, and Thakurtha, which was in 18, which focuses more on the theory, a theory version of this model. Today's presentation, today's coverage will be a little bit more focused on this model, just because I think it's a little bit cleaner, and you can kind of state some of the guarantees and get some of the ideas across clearer. But yeah, I'm kind of going to conflate the ideas that are contained in these various papers and sort of mix them all into one, mix them up a bit. But if you care about the specific details which are introduced in each paper, I recommend you check them out. And citations, of course, as usual, appear in the lecture notes. So this is another method of doing differentially private machine learning. What are the big differences? The big differences from DPSGD are the following. One is that DPSGD was sort of a modification of a very specific type of algorithm. It's sort of a white box method, but this is more black box. It's black box in the following sense. If you simply have some sort of private machine learning algorithm, or sorry, if you have some sort of non-private machine learning algorithm, then it can just simply plug into this and help you get privacy in this case. So this is quite appealing because of the fact that, in order to improve PATE and in order to get good PATE type guarantees, all you have to do, one of the main things, is make a good non-private learner. And we've already spent a lot of time as a community making good non-private learners. So this is convenient. So non-private learners help. They're sort of at the core, because we're just going to base our method off of non-private learners. Okay, so this seems like a great plus, just because of the fact that we don't really have to, do as much tuning in order to get good results in the private setting. But the downside is it works in a slightly different model. So recall before the model, when we were doing DPSGD, was we have some training data set, and the training data set is in fact totally private. It's totally sensitive, rather, in the sense that we don't want to leak anything about any of the training data points. However, in the PATE model, instead, in contrast, we're going to have it that there's a small set of training data. Sorry, there's going to be a sort of two sets of training data. There's private labeled training data, which is private in the sense that, it's sensitive, plus also some public, that is stuff which is okay to release publicly, that is not sensitive, unlabeled training data. So this is kind of picking up a little bit where we left off from the last part, where we not only have private data, private labeled training data, but we also need some amount of public unlabeled training data as well. So if you only have private training data, then this will not work. But yeah, so this is a slightly different model, which is why but it comes at a great benefit, since we don't really need, we can use some of our non-private methods in a black box way. So let me tell you a bit about some of the ideas before we talk a bit more about the details. So PATE, some of the key ideas work using stability-based ideas. So some of the keywords here, I'm not going to go too into detail for this last part of the lecture, but are stability, which we've already talked about a bit in lecture 10, where we talked about stability-based histograms and stability-based modes. And also, another key thing that comes up here is sample and aggregate, which we have not talked about, but it's kind of based around similar ideas. And this was a framework introduced by Nassim Raskodnikova and Smith in 2007. So what the sample and aggregate method does is it works using non-private methods, and it combines them in some way in order to make a private method. So roughly this can be broken down into two steps. One is to run a non-private algorithm, so NP algorithm on disjoint sets. And so, of course, naturally, since we're running a non-private algorithm, this is not going to have any sort of privacy guarantee. But the second thing is that we somehow, this is the sample step, like the name says sample and aggregate. So naturally, this is what we call sample. The second part is the aggregate step. And by that, we combine the results in some way, which is differentially private. So, and it turns out whatever combination of the results that you get, that will be appropriately differentially private, since you do it in a privacy preserving manner. So this is a nice approach because it is very general. It can run based on just a non-private algorithm for whatever problem. And if you have, say, a limited domain or something, maybe it's a binary outcome, or essentially in a lot of cases, except when it's like a continuous valued outcome, which can be a bit trickier maybe, you can really convert a non-private algorithm into a private algorithm without a whole lot of work. So it's very flexible. The downside of this type of approach is that it's typically a bit lossy, in the sense that in many cases the private complexity is going to be equal to like non-private complexity, the amount of data you need, times 1 over epsilon. So you kind of need a 1 over epsilon multiplicative factor more data, which is often not quite the best you can do. But yeah, this is the general framework. I'm only going over this very quickly, but it's a very powerful and general framework which has seen a lot of impact in a lot of different areas. So it might be something you want to check out. But yeah, just again to summarize it, there's two steps. One where we run the non-private method on disjoint data sets, and then we combine them in a differentially private manner. Yeah, the idea is that we're going to use our, like I said, this is going to use a non-private learner in a black box way. So we're going to run many non-private learning algorithms on disjoint data sets, and then we're going to, our aggregate step will be a stability-based histogram that will compute the mode in a stability-based way, which we discussed in lecture 10. But we're going to go into more of these details, so don't worry too much if it made not that much sense at this point. So you can see this figure, which describes what the PATE approach is. This figure is from the original paper by PAEGT. And we have the following type of model. So there is some set of sensitive data, which we have right here. This sensitive data is split into many different disjoint sets. So if we have a Okay, I guess we've previously used n for the total number of data points, but so a bit of a notation switch here. But what we're going to do is take our total data set, however many points we have, we divide it into n equal sized parts, and we use each of those training data sets in order to train a different classifier, a different machine learning model. These machine learning models will be called the teachers. And ideally, you know, given the magic and wonder of machine learning, each of these teachers should hypothetically be good. What do we mean by good? It means that, you know, they should, given a point from the test set, which is different from the training set that they've been trained on, it should be able to get pretty good accuracy, whatever that accuracy is, like 90, 95, something like that. Whatever, it's a problem-specific question. So, yeah, what are the odds that these would all be good? I guess it should be pretty good in general, just because if we have a lot of data in our sensitive training set, then we can just split it into n different parts, and even these sort of smaller data sets should be enough to train our teachers to pretty good accuracy. We don't need it, of course, to be quite as good as if we had the entire training set, but even some sort of lesser amount of data should still be good enough to get reasonable accuracy. So again, yeah, all we want really is that we have trained each of these teachers in a non-private way such that they'll be highly accurate on the data set. So, okay, we're going to build this up by step. Suppose the first sort of instance is, suppose we want to just make one private prediction. Note that this is a much simpler goal than what we focused on in previous parts of this lecture. In particular, what we wanted in the DPSGD setting was we wanted a private model. So the private model required us to output a parameter vector, which is totally differentially private. That is, you know, the weights for every single layer in the neural network, we wanted that to be differentially private. However, all we want this time is to be able to output a single private prediction. What do I mean by that? I mean that if you give this, I want to just, given some x, we want to give a prediction of the label of that, y hat, which is going to be differentially private. In contrast, training a full machine learning model would be able to answer any number of prediction tasks because we have the model in hand. So we can do whatever we want by post-processing, that would be okay. But at least for the time being, we're just going to focus on making one specific prediction. We'll see how to boost that into being able to make multiple predictions later. But yeah, suppose we just want to make one prediction privately. And in particular, in this private prediction model, we're going to assume that you know, the feature vector is public. So what are we going to do? Where does this fit into this whole framework? Well, what we're going to do is essentially, here in this diagram of the setup, what we have is sort of a gap. This is where the privacy gap is, in the sense that the adversary can see anything on the right side of this gap and not see anything on the left side of this gap. What's going to happen is we will ask this aggregate teacher to label an individual point. So again, we're trying, given x, the goal is to output y hat privately. So again, what the student does is they ask some aggregate teacher, what is the label y hat for this point? Now, what is this aggregate teacher? I haven't described it to you yet, but what the aggregate teacher is essentially, it will ask each of these teachers what the labels are. So for example, imagine, just to give a concrete example, because this might be a bit abstract for now, what the given data point, we could imagine we're in a setting where we're trying to label a point x. Is this a cat or not a cat? So what the student would do is ask this aggregate teacher, here's the point x, is this a cat or not a cat? And what the aggregate teacher would do is it would ask each of these non-private learners what they think. So for example, teacher 1, remember, is trained a full model on its data set, which is potentially sensitive. So it'll give the point, say, I don't know, cat. Teacher 2 would similarly do the same sort of thing, cat. Maybe teacher 3 would say not cat, but overall, a lot of them will say cat. So now we have a bunch of different predictions, and they all feed it into the aggregate teacher. So this would create some sort of, like, if we wanted to draw this as a histogram, so just to say, like, maybe, you know, let's say the breakdown here is 80% cat, 20% not cat. And so if we aggregate this, this would give us some sort of histogram like the following. So this is cat, not cat, like here. And as I mentioned, each of these predictions that we have right here at the bottom, those are not private in nature. This is a non-private histogram. But again, the very nice thing is that we know how to privatize this. Okay, so sorry, let me slow down a bit. So if we're in a non-private setting, what we could say is, okay, 80% of our classifiers here say this is a cat, so therefore naturally it's likely that this acts as a picture of a cat. However, this is of course not privacy preserving, and the question is, can we output the fact that 80% of these classifiers, non-private classifiers, said that's a cat? Yeah, how do we indicate that privately? And the way that we'll do it is using a similar type of distance to instability type framework that we mentioned in lecture 10. This was formalized a lot in a work by Thakurtha and Smith in 2013. But yeah, the question is, how do we in fact show that, how do we in fact output the fact that most of these said that it's a cat? And just to remind you about some of the stuff we covered in lecture 10, it's the following type of idea. It's using the proposed test release type framework in the following way. So the first thing we do is just look at the distance between the most frequent and the second most frequent element. And we note that this is some value, let's say, let's call this tau, I don't know. So we can see that this tau is very significant, and in fact, it's enough to say that, you know, C is more frequent than NC, but that's not differentially private. So instead, what we're going to do is essentially privatize this value of how big the gap is between the most frequent and the second most frequent element. So what we're going to do is essentially take tau, and then we add, say, Laplace noise. Note that this quantity, in fact, will be differentially private. Yeah, the sensitivity of this is not hard to see that it's 1. So, okay, now we've got a differentially private estimate of the gap between the largest thing and the second largest thing. So the idea is that what we do is we see if this is large. What that means is that equivalently in sort of words, there's a big gap between the mode and the second highest. So if there's a big gap between the mode and the second highest, then we can just output. Then we can output just the mode without any noise added. And this is great because if there's no noise, then we, like, of course, outputting an answer with no noise is precisely what we would want in differential privacy. So yeah, the idea is, just to summarize what I just explained, if there's a big gap between the most frequent label and the second most frequent label, then in fact it's easy to output whatever the mode is, and we can do it without noise. So therefore, the aggregate teacher, who took all of these individual predictions from the individual teachers, can privately output the correct mode and send that to the student. In particular, they provided the X, which is public, but now they get a privatized Y, which is a prediction for this label. So that's nice. And the question is, what happens if this isn't the case? What if there's not a large gap between the mode and the second highest element? Then we'll just output randomly. Otherwise random. And yeah, that's okay, because that's always going to be privacy preserving. Okay, so this tells us how we're supposed to, do a single prediction privately. Now, on the other hand, what if we want to, like, this is the basic thing, if we want to output, if we want to answer many classification tasks, or one classification tasks, what about many classification tasks? So the naive way of doing it is just literally do this all the times in a row. We know how to do one prediction. We know how to do advanced composition. So if we just do that naively, then advanced composition will essentially incur a cost of square root t. So if we want to do t classification task, we'll incur a cost of square root t times the cost of doing a single query. However, what instead we could do is instead use the sparse vector technique. So recall from a few lectures ago what exactly the sparse vector technique is. The sparse vector technique allows us to answer a bunch of queries is something above a threshold or below a threshold. And it allows us to answer this at a cost which is only square root c, where c is the number of things which are above the threshold. And so let me just write this: number of greater than threshold queries. So you might be wondering, how is this at all relevant? Why is it, why is there any sort of correspondence here? Well, the idea here is that if this sort of says that there's going to be two types of queries in the sparse vector setting, some of which are above threshold and some of which are below threshold, and we only have to pay a cost depending on the ones which fall into one of these two classes, the ones which are above threshold. So similarly, in this case, we're going to sort of assume that, all right, maybe most of our teachers are going to be accurate in general, and therefore, most of the time, the aggregate teacher will get a stable prediction. It's going to be relatively uncommon that we get an unstable prediction. So in other words, because we only pay a cost here, which depends on the number of queries which are above the threshold, which we think is going to be a somewhat rare event. If we can make this a rare event, then we'll pay a low cost. We want to try to make this correspond to the cases here where the teachers are unstable in terms of what their predictions are for the point. So let's say, essentially what we're trying to do is say that the number of above threshold, we're trying to do a correspondence here with which queries are unstable. And essentially, if we can do this right, then, and most queries are in fact stable, which is likely if we have some good non-private classifiers, then we can say that we pay a low cost in order to do a sequence of private classification tasks. So really, our queries will be sort of the following form, just to say it in words. If we tried to classify this image using n classifiers, is the gap between the most and second most likely prediction that they provide significantly large? That'll be the type of query that we feed into sparse vector. And depending on whether it is above or below that threshold, if it's above the threshold, that means if you do the correspondence in the right way, being above the threshold corresponds to the gap not being large, so you can just output randomly. And on the other hand, if the value there is small, then you can just output, then it means that the gap is large, and then you can output the mode without noise. So this is how we're going to significantly reduce the cost of a sequence of queries. Yeah, just based on the fact that most of them are going to be stable, and if we only pay the cost depending on the unstable ones, we're going to save a lot. Okay, so we went from one classification task to many classification tasks. But now the final thing is actually training a classifier. And this might seem like weird. How did we get from what we were doing before into a private classification, training a private classifier as a whole? The intuition is the following. Again, we saw how to do a single private prediction task. Each of those would give us some xi, yi hat pair. Note that this is public data. This is public. So we're okay with sharing this with the world. And this is privatized. By that I mean it's based on, you know, some private training data, but it's appropriately privatized. Or let me say it a different way, because this I think private and private. It's a privacy preserving prediction. So in other words, it's okay to release this whole point xi, yi hat to the public. There's not going to be anything bad about that. So okay, that's one thing. Now, similarly, imagine we're in this case where we're doing many classification tasks, and we get x1, y hat 1, and then we get x2, y hat 2, and so on. These are all private and sensitive, these are all privatized in the sense that these can be released to the public without future privacy loss. And the really nice thing here is that we now have a, in some sense, synthetic data set. What do I mean by that? In the sense that this is a whole bunch of labeled training data, which is privacy preserving. You know, it's appropriately privatized, and by the guarantees of differential privacy, we can do whatever we want afterwards. And we can't sort of, by post-processing, we can't reveal anything new about the sensitive data set. So in short, the results of these many classification tasks, which we hypothetically run on our data set, will be you know, a synthetic data set, synthetic private data set. So yeah, this is nice, because what we can do with a synthetic private data set is feed it into a non-private learning algorithm. So with the synthetic private data set, you know, feed into a non-private learning algorithm. And this will give us some sort of, you know, trained private classifier. So I think that's quite a nice type of framework. In particular, it starts off just by doing privacy preserving predictions. You do a prediction using this type of stability-based idea. After you do a sufficient number of these predictions using an appropriate sparse vector stability-based idea, you're going to have some sort of sequence of privatized classifications, and that'll give you some synthetic private data set, which you can then feed into a non-private learning algorithm. And this will allow you to train a private classifier. So those are some of the core ideas here, and these can be, you know, refined, and they are refined in the original PATE paper in order to make a real system which is quite effective practically. So yeah, that's essentially the whole PATE framework. And that concludes our lecture on differentially private machine learning in kind of modern settings. You can see I presented 2 different types of machine learning frameworks in order to try to do private machine learning. But yeah, there's really a lot more to the story, and this is a very active area of research right now. So if you're interested, I encourage you to dig into the literature and see what else has been done, and maybe you can contribute some ideas of your own.